Okay, welcome to today's lesson on solving polynomial inequalities. The last several days we've been looking at polynomial equations. And what we're going to notice now with what we're looking at is rather than an equal sign, we're actually going to have an inequality sign. What it's asking is for what values of x is x squared plus 3x minus 10 going to be less than 0. Okay. Now the question will be, well, how are we going to solve this? Because this is not an equation, so our approach is going to be similar to what it would be for an equation, but not quite the same. Okay. Now what we actually have are a couple of options for solving this type of situation or this type of inequality. The first being to graph the function. Another alternative, which tends to take a little bit longer, is to solve algebraically. So what we're going to do for this particular question is attempt to solve it graphically. So if I picture the function, and it's written above, y equals x squared plus 3x minus 10. If I picture factoring the right side of that expression, or that equation, what I'd be looking for are two numbers that multiply to negative 10 and add to 3. So as it turns out, we'd have y equals x plus 5 times x minus 2. Okay. Now for the x-intercepts, okay, and this is sort of going back to more Unit 1 material. So for the x-intercepts, we have to set y equal to 0. So if I did that, now it just looks like an equation we've been solving the last few days, and then we'd say, okay, well, if I set each factor equal to 0, I'm going to get two roots, negative 5 and positive 2. Okay. Other things we'd want to consider if we were going to sketch this function or do a graph of it, we'd want to know where the y-intercept was, and we'd also want to know the end behavior. Okay, so the y-intercept, as it turns out, the equation we were given initially is actually in standard form. So as it turns out, in standard form, the constant term at the end is actually representative of the y-intercept. So our y-intercept is negative 10, and then the last thing we want to identify is the end behavior based on the leading coefficient on the x squared being a positive 1. We would know that this has to rise at both ends. Okay, so this is what the graph would look like. Now we'll highlight here where the two x-intercepts we determined are. So we found at negative 5 and at positive 2, we're supposed to have x-intercepts. And if you actually look at the graph at this point, you're going to notice, well, anywhere to the left of negative 5, my graph is above the x-axis, and anywhere to the right of positive 2, it is also above the x-axis. The inequality was looking for where this function was actually less than 0. So the area of interest is actually, I'm tracing it here in red, it's actually the area of the graph that's below the x-intercept. And if I look at what interval that is, it's basically anywhere between negative 5 and positive 2. Okay, so as far as a solution, our conclusion to this question is, so therefore, and the way we're going to write this solution here more formally kind of looks like a statement of the domain, because we're basically saying x such that needs to be between negative 5 and positive 2, and that any real number between those values would work. Okay, so having finished that first example, what we're now going to look at, because we didn't do it in the first case, was the basic approach we're going to take if we're asked to solve an inequality like this algebraically instead of graphically. Okay, so the basic idea will be, if we're asked to solve an inequality algebraically, there's four main steps that are involved. Okay, so the first step would be factor the expression. Now we do need to make sure that we have 0 on one side of the inequality. It doesn't matter which side it's on, but it has to have 0 on either the left side or the right side. So after you've factored it, what you would want to do, temporarily at least, is pretend the inequality sign was actually an equal sign, just so you could picture what the roots of the expression that are there would be equal to. Okay. Now the next part would be to graph the roots on a number line. That's not really graphing the function. We're going to see what I mean by graphing them on a number line here momentarily. And then once we know the intervals we're sort of looking between, we use test points. So basically picking values of x that would fall within each interval and noticing the behavior of the expression, whether the result is a positive number or a negative number, and we have to compare that result to the actual inequality, right? Okay, so example 2, what I'm actually going to do is solve it algebraically, but then also do a quick sketch of a graphical solution to it, just to sort of support the answer. Okay. Now we don't want to leave it in that form. We want everything on one side and 0 on the other. So we want to rewrite this as x cubed plus x squared minus 14x minus 24, and that is greater than or equal to 0. Okay. What I would do from there is I would actually look at the polynomial that's on the left side and say, okay, I need to factor it, but how am I going to do that? Okay. Unfortunately, we're not going to be able to group terms here, so this is going to be a case where we're going to use factor theorem. Alright, so what we would want to do is now establish, looking at the left side there, what the roots would be. Remember I'd said in the steps earlier, we're going to kind of pretend temporarily that that was an equal sign, not an inequality sign, to imagine what the roots are. So our roots would be -2, -3, and +4. Okay, what we're going to do with those is now create a number line. Okay, so I've numbered basically the values that are here. What I can do as well, so picture there would be a root here, a root here, and a root here. What we now need to sort of picture or envision are some values of x that would be between each of these roots. So if I looked to the left of -3, okay, basically any number would work. We don't need to use a really big number, but what we could do is say, well, let's try, or let's test a number like -4. Okay, that is going to be less than -3. Similarly, I'd look between the next two roots, -3 and -2. Unfortunately, we're going to have to use a decimal here, but one that would make sense would be -2.5. Okay, between -2 and 4, any number within that interval would work. A nice one to use, for instance, nothing wrong with using 0 there. Okay, and then the last interval I'd have to consider would be, well, anything greater than 4. So, for instance, nothing wrong with using x equals 5. Okay, so what we would now need to do is, there are 4 intervals. Okay, so we're going to test the intervals that we have. Okay, now what I like to do is number the intervals. So the first interval, and which direction you work from, I'm going to work left to right. So my first interval would be for x less than -3. Okay, so we're testing -4 here and seeing what happens. Okay, so I'm going to evaluate f of x at -4. Now what we can keep in mind, this will save us some time, we have that expression in factored form now. So I'm just going to insert into this expression here the test value in each case that I'm using. Okay, so I'm going to say, okay, well, that would mean -4 plus 3, -4 plus 2, and -4 minus 4. Okay, now ultimately, I don't really care what the number that I get is equal to. I'm more concerned with whether the number is positive or negative. Okay, so if we break down each bracket here, okay, -4 plus 3 would end up being a negative number. Okay, -4 plus 2 would also be a negative number. -4 minus 4, also a negative number. Okay, if I multiply 3 negative numbers together, I get another negative number. Okay, so what I would know is the product there is actually less than 0. Okay, now keeping in mind what the inequality itself said, so if I go up for a second here, our original inequality was looking for values of x that made f of x greater than or equal to 0. Now, the test value that we just looked at produced a value that was less than 0. So that does not satisfy the condition. Okay, so this is not a solution. Okay, so then we would go on to and test our next interval. So the next interval is going to be between -3 and -2. So the value we said we could try, picture -2.5. So if I insert that into each of my brackets here, we have to think what would happen. Okay, now in the first bracket, -2.5 plus 3, that is actually going to be a positive number. It's positive 1/2. Okay, -2.5 plus 2, that's a negative number. Okay, and then my last bracket is still negative. As it turns out, a positive times a negative would actually be something greater than 0. Okay, now I was looking for something greater than 0, so this is actually going to be a solution. Okay, for 3, the third interval. The third interval is saying between -2 and 4, we were going to try, we said 0 here. Okay, so picture 0 plus 3, 0 plus 2, and 0 minus 4. Okay, similarly, if I picture first bracket and second bracket are positive, third bracket is negative, the result would be a product less than 0. That is not going to be a solution. And then lastly, my fourth interval, which was basically any value of x greater than 4. So we said let's try 5. So picture 5 plus 3 times 5 plus 2 times 5 minus 4. All three of those expressions are positive, meaning the product is positive, so that interval is also a solution. We could say, therefore, the solution to this inequality is x such that, now what we need to recognize here, we're actually going to include, and this is a little different from the last example, because the actual inequality specified that x could be greater than or equal to 0, that I could have x greater than or equal to -3, less than or equal to -2, or x greater than or equal to 4, because 0 is an acceptable answer here. In the previous example, we had to be less than 0. Just to think graphically here, just as a support to this answer, okay? So what we'd have, so picture The equation we'd have to envision graphing would be x plus 3 times x plus 2 times x minus 4. We'd already know the roots. They were -3, -2, and 4. The y-intercept, now to save a bit of work here, it ends up being -24. The reason for that being, if I could scroll up to the top for just a quick second, notice that in our original expression there was a constant at the end. That's our y-intercept. Okay. The alternative is you end up just plugging in 0 for x and solving, and then because there's a positive lead coefficient, this rises to the right and falls to the left. Okay. Now there's a graph of a very rough sketch of this function here, just for our reference. Okay. You'll notice if I'm looking, where is this greater than or equal to 0? Notice that there is a turning point above the x-axis between -3 and -2, and then my function continues on above the x-axis beyond x equals 4. Okay. So in red, those are our solution intervals.
Okay, so for example B, what we have is a quartic function, and again we're going to go through the motions. We want to try and factor it down and see where those roots are, and we can do a whole bunch of interval testing and doing those test roots. So with this quartic function, I take a look. It doesn't look like we can do any kind of factor by grouping, so unfortunately we're forced to use factor theorem. So we'll go ahead and define our function as above there. So f of x equals x to the power 4 minus 2x cubed minus 8x squared plus 18x minus 9. And again, do some test roots, that's things that will divide into -9. So we will try our test root of 1. The reason that I wanted to do this example B with you is because even though we've done synthetic division, we do have a cubic in the second bracket here, which needs to be factored further. Lucky for us, though, we do end up with a nice looking cubic here, because when we go ahead and try to factor this, it looks like factor by grouping will work. So we'll take that approach. So when we go ahead and factor some more, if I take a look at the first group that I've defined there, I can factor out an x squared, which would leave me with an x and a minus 1. And in the second group, we can take out a -9, again leaving me with an x minus 1. And remember, the key to factor by grouping is that the brackets need to be the same. And we do have a minus 1. We do have an x minus 1 in both brackets. So what we'll do is common factor out the x minus 1, leaving us with x squared minus 9. And again, the key to factoring is take a look at each one of your brackets and see if you can factor further. That x squared minus 9 at the end is now a difference of squares and can be factored further. So last step, x minus 1, and actually we have x minus 1 twice, so I'm going to call that x minus 1 squared, and then we'll factor out the x squared minus 9, leaving us with an x minus 3 and an x plus 3. Okay, so our f of x is fully factored. What we want to do is state the inequality. So x minus 1 squared, the x minus 3, and the x plus 3 is less than or equal to 0. Okay, so our original question has went from standard form, which you see up at the top there, to factored form. Okay, so to solve algebraically this inequality, we want to state the roots. So the roots here are that x equals positive 1 and then plus or minus 3. And those roots end up going on our sine line. So there's our line, and we'll place those roots on the line. So there's negative 3. We'll just kind of space them out, eyeball it. There's positive 1, and there's positive 3. So again, like in the last example, as Mr. Wheeldon has shown you, you want to test values that are in between these intervals. So for example, a number less than negative 3, we could test x equals negative 4. In between negative 3 and 1, the easiest value to test would be 0. In between 1 and 3, we could test the value of 2. And finally, greater than 3, we can pick any number. We'll just go with 4. In our first interval, the one that is less than negative 3, we said we were going to test the value of negative 4. So, in our factored form here, we're going to sub in the value of negative 4. Negative 4 minus 1 squared, negative 4 minus 3, and negative 4 plus 3. Now when we go ahead and do that, again, we don't care what the actual value is. We just want to know whether it's positive or negative. Now in this first bracket, no matter what we get, in this case we get negative 5, but no matter what we get, we have to square that number. And anytime we square a number, the value or the number becomes positive. So this bracket is always going to be positive because of that exponent 2 there. Now in the next bracket, we have negative 4 take away negative 3. That's going to be a negative number as well as the last bracket. So if we were to multiply a positive number times 2 negative numbers, our final product would be a positive number. Now again, you need to think to yourself, the original question said, when is this less than or equal to 0? So in this case, anything in that first interval, so anything in the interval less than negative 3, would not be a solution because we're looking for less than 0, or less than or equal to 0, not greater than 0. So let's try the next interval. So the next interval we're looking for is in between negative 3 and positive 1. So we decided that we're going to use the value of 0 to test that interval. So if we go ahead and subbed in 0 into our x, again, the first bracket would end up being a positive number, the next bracket would be negative, and the third would be positive. And if we went ahead and multiplied 2 positives and the negatives, we would end up with a number less than 0. We would end up with a negative number. And again, this would be a solution because we are looking for values less than or equal to 0. For our third interval, we are testing values in between 1 and 3, and we decided on using the test value of 2. So subbing that in, would leave me with, again, a positive number for the first bracket, negative for the second, and a positive for the third. If we multiply 2 positives and a negative, we indeed get another solution. And the last interval that we need to test is anything greater than the value, anything greater than our root of 3. So we decided on using the test root of 4. Subbing that in, gives us with all positive numbers, and the product of all positive numbers is a positive number itself. And knowing that we're looking for anything less than 0, this is not a solution. So therefore, the solution to the inequality is x such that, so the first Okay, so the solution to this inequality would be, again, because we are looking for anything less than or equal to 0, our interval should have that less than or equal to symbol. So x such that we had in between -3 and 1, and then our other interval was between 1 and 3. Now, is there any way that we could maybe combine these? Taking a look at the end of this first interval and the beginning of the second interval, they happen to be the same. So essentially, what your solution really is between -3 and +3. And this will become more clear once I show you the graphical solution. If you were asked to do this question graphically, again, you would find your x-intercepts, which we found above, which were the roots. The x-intercepts were 1 and plus or minus 3. The y-intercept, again, comes from the very last number in standard form, which was -9. And then the end behavior is determined by the degree of the function, which is a quartic, and because our leading coefficient was positive, both ends will rise. So we have a root at 1, and a root at +3 and -3. Now, something important to note about the root at 1, I'm just going to scroll up a little bit to our factored form. Taking a look at our factored form, we have the exponent 2 here. And this tells me that the root of 1 is going to be a double root, or a turning point. So something important to note when we're graphing. Okay, so we've plotted our roots. Our y-intercept is somewhere down here at -9. And then we go ahead and graph, keeping in mind that both ends of this function are going to rise. So it would look something like this. Remember, the 1 is a turning point, so it just bounces off the x-axis. There's our graph, and again, we want to know when this graph is less than or equal to 0. So if we take a look at our graph, anything below the x-axis would be in red here. So our solution would be that. So kind of tying into our algebraic example, the solution is in fact in between -3 and +3, as we have stated above. Now for the very last example, we have 6x cubed minus 13x squared plus x plus 2 less than 0. What I would like for you to do at this point is try it out on your own and see how you do. I will post the solutions on video and make sure you try to get exactly what we have. And if you have any questions, then make sure you ask in class. And that's it for today's lesson. Again, I'll reiterate, make sure if you have any questions, come see the teacher tomorrow and ask questions. That's it for now. Take care, guys.